All right, welcome back. In this video, we'll be finishing up chapter 5 by looking at the Poisson distribution. So this is yet another discrete distribution. In section 5.2, we were looking at the binomial distribution. Here we have one more discrete distribution called the Poisson distribution. So the story goes like this. For a binomial experiment, you want to know the probability of getting a certain number of successes in a given number of trials. What the Poisson distribution helps you with is if you want to know the probability of getting a certain number of occurrences in a given unit of time or space. Book's definition, Poisson distribution applies to occurrences of some event over an interval. So if you wanted to find the number of occurrences over a length of time, like the number of cars that arrive at a stop sign over the course of an hour, the area, like the number of typographical errors occurring on a physical page of text, or volume, if you want to find the probability of finding a certain number of impurities in a room of a certain size, in a volume of air. So the interval can be time, distance, area, volume, or some similar unit. And then we're going to have a formula for that probability, as we'll see. So some sample problems. Suppose that the mean or average number of oil tankers that show up to a port city is 8 per day. We would like to know the probability that more than 8 tankers will arrive in a day. Here, in this case, the arrivals of the tankers occur on an interval of time. So that's a Poisson distribution. 2,000 trout are introduced into a lake having a volume of 20,000 cubic meters. We want to find the probability of finding 3 trout in 1 cubic meter of the lake. Okay, so those are sample problems we might encounter in this section. Like the binomial distribution, the Poisson distribution has some requirements, so we'll look at those. The random variable x needs to be the number of occurrences at some event over an interval. The occurrences have to be random, of course. If the tankers arrived at a port like every hour on the hour, then for one, that wouldn't be very interesting, and for two, we couldn't use this distribution. The occurrences should be independent of another. So in the probability of finding the trout in a lake problem, we're going to assume that the trout don't hang around together or go in groups or anything like that. The occurrences need to be independent of each other. The occurrences need to be uniformly distributed over the interval being used. All right, so that said, here is the formula for this. So let's break down the formula first. So the P of x stands for probability of getting x occurrences, and then it's a fraction. The denominator of the fraction is x factorial. We saw the factorial when we were developing the combinations formula and looking at the fundamental principle of counting. For the numerator, it's a product of mu raised to the x power, where mu is the mean number of occurrences of the event over the interval. And then the next expression is e raised to the minus mu power, where e is the base for our system of natural logarithms, approximately 2.71828. So if you took intermediate algebra, you should have learned something about the e to the x function, the natural log function, and so forth. Here, we're not going to need as much as you probably learned in that class. The main thing that you're going to need to know is that e is about 2.71 and how to raise e to a power, which is going to be that mu. So let's try to use the formula to answer this question. So here it says the mean number of accidents per month at a certain intersection is 3. We would like to know the probability that in any given month, 4 accidents will occur at this intersection. So for this one, the mu is 3. That's the mean number of accidents per month that occur. And so we'll have P of x is equal to mu, that's 3, raised to the x, e to the minus 3 over x factorial. So that's the general formula for this Poisson distribution. We want to evaluate it for 4 accidents. So we need P of 4. So that will be 3 to the 4th power times e to the minus 3 over 4 factorial. So let's calculate that. Let me give you an answer. All right, so I'm getting about 0.168. So notice that the Poisson distribution is really only dependent on the mean mu, and the rest of it, the x, is the input to the function. So the e to the minus 3 was a constant for this, and so we just had to replace the variable x in 2 places. So we'll try another example here in just a moment. All right, so that's our first example. Before we go on to our next example, I wanted to mention that some books use a different letter than mu for this. Some books will use yet another Greek letter lambda, which looks a little bit like an upside down y. They'll use a lambda in place of mu. So they may write mu raised to the x power, e to the minus lambda over x factorial. So we'll use the mu character because that's what our book does. But if you're looking on Google or in other books or something, you may see a lambda used in place of mu here, but it's going to mean the same thing. All right, next example. A newspaper finds that the mean number of typographical errors per page is 4. So for this one, our mu will be 4. We want to find the probability that exactly 3 errors will be found on the page. So here, if our mu is 4, we want to know P of 3. So we'll have 4 to the 3rd power, e to the minus 4, and then that will be over 3 factorial. So once again, we'll look to our calculator. And then we'll get about 0.1953. For the next one, we want to know the probability that at most 3 errors will be found on a page. Normally, like in a binomial distribution problem, if we wanted to know at most questions, or at least, we would think about using the complements rule. And the thing with the Poisson distribution is that there is no upper limit, so we can't really use the complements rule for this. So at most 3 errors would be 0, 1, 2, or 3. So we're going to figure out those 3 probabilities and add them up. So for 0, let me write it. P of 0, P of 1, P of 2, and P of 3. So give me a second to put that down. All right, so I've filled in the formulas for each of these. Notice that we have basically the mean raised to the x value, e to the minus the mean, divided by the x value factorial. So we end up with 4 of these, one for 0, 1, 2, 3. And so to calculate this, it actually will be easier for us to factor out that e to the minus 4. That'll just make it a little easier to type into the calculator. And a lot of this, we can do this arithmetic in our head. 4 raised to the 0 power is 1, and 0 factorial is 1. So this first term will be a 1. 1 factorial at the bottom is a 1. Up top, we've got a 4, so there's a 4 here. Then 4 squared is 16. 16 divided by 2 is going to be 8. And lastly, we'll have 4 cubed, which is 64. And then 3 factorial is 6. So we'll have 64 over 6. All right, so doing that will just give us a little bit less typing to do. Of course, you're welcome to do all that on your calculator if you want. So this will work out to be about 0.4334. So now, if we want to know the probability that more than 3 errors will be found on a page, notice for this one we are able to use the complements rule because there are either more than 3 errors or not. If there are not more than 3 errors, that means that there are at most 3 errors. So we can just take the complement of the result we just found, getting 0.5666. So make sure you take some time to make sure you understand why we weren't able to use the complements rule for part B, but we are able to use the complements rule for part C. Okay, this next example comes from our textbook. So here it says radioactive atoms are unstable because they have too much energy. When they release their extra energy, they are said to decay. When studying cesium-137, a nuclear engineer found that over 365 days, 1 million radioactive atoms decayed to 977,287 atoms. So the difference there, 22,713 atoms decayed during the 365 days. So for part A, we need to find the mean number of radioactive atoms that decayed in a day. So this is simpler than it sounds. If we know that 22,713 decayed in 365 days, then all we have to do is divide to find out the rate of decay per day. So this will give us about 62.227, let's say 62.2 atoms per day. And that would be our mu. So now for part B, we want to find the probability that on a given day, 50 radioactive atoms decayed. So that's P of 50. So then using our Poisson formula again, 62.2 raised to the x power, that's 50 this time, e raised to the minus 62.2 divided by 50 factorial. So don't try this without a calculator or computer of some sort. Let's see what this turns out to be. Be very careful how you type things in. All right, about 0.0156. Okay. All right, so make sure you take some time to take a look at this question and ensure that you understand it. All right, so now we're going to answer the trout question. Here it says 2,000 trout are introduced into a lake having a volume of 20,000 cubic meters. We want to find the probability of finding 3 trout in 1 cubic meter of the lake. So the first thing to do is to know the mean, right? The formula for the Poisson distribution is P of x equals mu raised to the x power e to the minus mu divided by x factorial. So it's totally dependent on what the mu is. So your first step almost always is to figure out what is that mu and then go from there. So the mu would be the rate of occurrence of the trout. So we're told that there are 2,000 trout per 20,000 cubic meters, or that's 0.1 trout per cubic meter. Of course, it seems funny to say 1/10 of a trout, but you could think 10 trout or 1 trout for every 10 cubic meters, if that's easier for you. All right, but our mean is going to be 0.1, and we wanted to find the probability of getting 3 trout in 1 cubic meter of the lake. So our mean is 0.1. We'll need that to the 3rd power, e to the minus 0.1. And then again down below 3 factorial. So let's see what we get. Okay. So that's about 0.000151. All right, so really small chance. And if we think about it, let's try to make sure that that really small probability makes sense. We're told that we should expect basically 1/10 of a trout per cubic meter, which again is kind of hard to think of, but this says 1 trout for every 10 cubic meters. Here we're trying to find the probability of finding 3 trout in 1 cubic meter. So 3 times as many trout in 1/10 as much water volume. So that's going to be pretty unlikely. And so I think that's consistent with the probability that we found. Okay, so next up, we want to consider the parameters for the Poisson distribution. And very luckily for us, the formulas are really easy. We already have the mean, it's mu, and then the standard deviation is going to be the square root of the mean. So pretty straightforward. So for the trout example we just had, the mean is already done for us. It was 0.1. And then the standard deviation is the square root of the mean. And that is about 0.316. Okay, so the mean is the mean, and the standard deviation is the square root of the mean. So this is probably one of the easiest formulas we have in the chapter. That's nice. As in our earlier work, we can use the mean and standard deviation to help us decide if we're dealing with an event that is unusually high or unusually low. So let's try that. Actually, there was one other thing to do first. A Poisson distribution, the difference between that and a binomial distribution. For a binomial distribution, it's determined by the sample size, n, that is how many trials are done, and the probability of success. But a Poisson distribution is solely determined by the mu. For a binomial distribution, the possible random values or values of the random variable are 0 through n, which is the total number of trials, but the Poisson distribution doesn't have an upper limit. Okay. All right. So here, let's say that we know that the mean number of accidents per month at a certain intersection is 3. We want to know the probability that in any given month, more than 2 accidents will occur. So we don't have a way of saying, well, 3 or 4 or 5 or 6. So instead, if we want to know the probability of getting more than 2 accidents, then this will be 1 minus the probability of getting up to 2. So 2 or fewer. Okay, so think about it. It's 0, 1, 2, 3, 4, high number of accidents. We really want to know the probability of getting more than 2, which would be anything 3 or higher. The complement of that would be 0, 1, or 2. So let's find the probability of 0, probability of 1, and probability of 2. All right, so I filled in the details. We wanted the probability that more than 2 accidents will occur, and that turns out to be the complement of 2 or fewer. So I figured out the probability of getting 2 or fewer, which is 0, 1, or 2. Filled out the formula for 0, for 1, and for 2. And then gone through the calculations. It works out to be about 0.424. And so the last piece is just to get the complement part done. So we'll have 1 minus 0.424. And that works out to be about 0.576. Okay, so let's think about that, see if that's reasonable. We're told that the mean number of accidents per month is 3, and we want to know the probability of getting more than 2 accidents. Well, if the average is 3, then we should think it should be reasonably likely that you could get more than 2 accidents. So that makes sense. All right, so now we want to know if getting more than 4 accidents per month, would that be considered significant or not? So as a reminder, our mean is our mean, and our standard deviation is the square root of the mean. So we want to know if 4 accidents, is that more than 2 standard deviations above the mean? So we saw that our mean was 3. Our standard deviation is the square root of 3, which is about 1.73. So 3 plus 2 1.73s is about 6.46. So more than 4 accidents per month is not going to be, well, more than 4 would be 5 or more. So the number that would be significant would be 6 or more. 6 or more would be significant. Because that would be 2 or more standard deviations above the mean. Actually, 6.4 is not more than 2 standard deviations above the mean. It would have to be 7. 7 or more would be significant. Okay. All right. So last bit, and then we're done. We can use the Poisson distribution to approximate the binomial distribution in certain circumstances. We saw that the binomial distribution we're required to calculate using that combinations formula and do some raising decimals to relatively large powers. When that can be hard, and back before calculators were prevalent, it was more hard. But when that's hard, we can use the Poisson distribution to do the approximation. So what's needed in order for us to do this? The n needs to be relatively large and the p needs to be relatively small. So the number of trials has to be at least 100. And then the probability of a success, which was p, multiplied by the n, number of trials, has to be relatively small. And if you think about it, if we're requiring the n to be at least 100, and we're requiring NP to be pretty small, then the P must be itself pretty small. Okay, if both of these requirements are satisfied, we can use the Poisson distribution to approximate binomial. So the mu in that case is going to be N times P. Okay, so let's see an example. So firstly, we're going to use the binomial distribution, and then we're going to compare the result we get using the Poisson to approximate. So here, a glass manufacturer finds that 1 in every 1,000 glass items that they produce is warped. We want to use a binomial distribution to find the probability of finding 5 defective items in a random sample of 6,500 items. So using the binomial formula, out of 6,500, 5 will be defective. The probability of 1 being defective is 0.001. That's the 1 in 1,000. We need that to occur 5 times. The probability of not having a defect then is 0.999, and that has to occur 6,495 times. Okay, so let's go ahead and calculate that. Depending on your calculator, it may or may not be able to do this combination. So let's see if mine will do it. Okay, it's a really large number. All right, so that is a super tiny number. Let me make sure I typed it correctly. right, so sometimes it's worthwhile to double check, take a few minutes to double check and make sure that your typing is correct. So it looks like it should be about 0.145. All right, so about a 14% chance of getting 5 defective items. So let's think about that, check and make sure that makes sense. 1 in 1,000 is warped, so that makes sense that we could expect about 6 in 6,000. So having only 5 in 6,000 items, that's not completely unlikely. So that seems reasonable. And now we want to use the Poisson distribution to do this approximation. So the n is 6,500, the p is 0.001, the np, which is our mu, is then going to be n 6.5. So our mu, which is np, is 6,500 times 0.001, and so is 6.5. All right, so now we wanted to know the probability of getting 5 defective items. So this, we'll use the Poisson formula for this. The probability of getting 5 defective items, that will be our mean, 6.5, raised to the 5th power, e to the minus 6.5 power, and that's divided by 5 factorial. So the calculations here should have seemed easier for you. Let's see what we get. All right, so I'm getting about 0.1453688. Let me put more decimals out here just so we can compare. And then our other one, all right, so that works out to the same, out to about the 5th decimal place, almost. All right, so it's pretty close, and that was the point. When our n is relatively large and our p is relatively small, we can use the Poisson distribution to approximate the binomial. All right, so that takes us to the end of 5.3 and also chapter 5. Let me know if you have any questions, and have a great day.